Hi, everyone. My name is Zach Penrod, Sales and Marketing within Motion. Welcome to this session, taking a look at electrifying outdoor power equipment. With me today, we have Mark Connors, the Director of Engineering at DR Power. He's got plenty of experience within the area. And throughout the session, please utilize the Q&A tab on the top right so you can easily track some of the questions. With that, I will turn it over to Mark.
All right. Well, good afternoon or good morning, everyone, or wherever you are. Like Zach said, my name is Mark Connors. I'm Director of Engineering at DR Power. I've been here about 2.5 years. And really, since I've been here, we started this journey of electrification. What I'm going to do today is kind of talk through that, really share some lessons learned. We I'm not an expert by any means. I won't be giving you any probably earth-shattering information. But really, what we're trying to do here is just share our story, as an example of an electrification strategy. Give some of our lessons learned and really kind of invite a conversation towards different approaches and different technologies that we could apply. So I'm hoping to make this a little bit interactive. Hoping the Q&A can open up some discussion about strategies that other folks have taken. But I'll start with a brief introduction of our company, talk about a little bit about the driving forces of why we're getting to electrification, talk through the meat of this is really kind of where we've been so far and our strategy for developing electrification, and then conclude with some lessons learned. So quick overview of DR Power, Vermont-based company. Down there in the lower left, Dick Raymond started it all with a company called Country Home Products back in 1985. Classic catalog sales back in the day. Really started to move into power equipment with our flagship product, which is a walk-behind trimmer. So kind of basic idea of taking the string trimmer, putting it on wheels, so you take the pain out of somebody's back. We've worked through a variety of those models over the years, improving our gas powered, and we have dabbled, more recently in an electrified version, but that really wasn't a product that we fully developed here in house. Our other flagship product really is a field and brush mower, kind of the big brother of the trimmer. For maintaining larger properties, maintaining trail systems and things like that. So you can see the original machine here, quite different than our latest gas-powered version, with a fully hydrostatic transmission and basically a zero-turn machine. And then its companion, the first fully electrified version, and we'll talk about this more. This is really the basis of a lot of what we'll talk about today is how we got through here. And then mowing is a big category, in the industry, but something we really haven't been a big player in. We dabbled a little bit, back in 2003, we were one of the first to market with a battery electric mower. We've had some walk-behind gas-powered equipment, but we really jumped in with both feet a couple of years ago and acquiring Mean Green Mowers. Mean Green's a company out of Ohio that has 10 years of experience in commercial electric mowers. So that's been a big part of our kicking our electrification strategy into high gear. And in the lower right, you can see one of the first products we put out in partnership with them. Is the first zero-turn mower that DR Power ever made. So a little bit of overview of the company. We'll get into more of the products later. Want to jump in quickly to why we're looking at electrification. The environment's the obvious one. There's been other talks so far in this conference that touch on similar topics. But I think what's interesting in our case is when you look specifically at what's called small off-road engines, as defined by California Air Resources Board, has done a lot of research on this topic and is really leading the charge on a lot of fronts. It's interesting to note that one of their studies shows that an hour of use with a typical lawnmower, walk-behind lawnmower, is equivalent to 300 miles in a car, right? So that's driving LA to Vegas. An hour of using a leaf blower is equivalent to 1,100 miles in a car, so LA to Denver. So it just shows really how inefficient, how dirty small engines still are relative to the big strides that have been made in automobiles. Small engines, and particularly two-stroke small engines, is which what we're talking about here, are very are far behind. And there really just isn't the opportunity to improve them a lot further because of the size and the market forces and other things are just always going to work against that. But there are a lot of them out there, and that's what this chart shows, is that there's 12.9 million just in California small engines in residential lawn and garden. So that's really leading to a lot of regulation and also incentives. So classic government stick and carrot approach, right? So California has passed a bill that will ban the sales of certain outdoor power equipment with engines greater than 19 kilowatts, or I'm sorry, smaller than 19 kilowatts, so approximately 25 horsepower. Those will be banned for sale for commercial use starting in 2024. So that includes most lawn and garden equipment, portable generators, and pressure washers. So that's a good portion of what we sell at DR Power and our parent company, Generac. And CARB's position there is really part of an overall strategy to reduce or to go to zero emissions on off-road equipment by 2035. So that's the stick, but there's also the carrot. They have provided incentive programs. So the California Core program, which you see here, offers incentives of rebates up to $12,500 for commercial. And also, at the federal level, the Inflation Reduction Act has portions of it which provide similar rebates for commercial mowers. So we are seeing movement on both sides of that stick and carrot front. But one of the things that we're really focusing on as a business is the user experience, and we're hoping that will really drive sales in the long run. So we'll talk more about a lot of these, but emissions, noise, and vibration are a big one. And some of the studies that we've done recently on the first product that we put out there, the field and brush mower, show that there's pretty good reductions in sound. You're always going to get sound from the blades. So when you look at here in the lower left, this is the gas version at full throttle and the electric version. So a decent reduction in sound levels with the blades running. When you look at that without the blades running, it's an even better reduction. And you can see here, if you look across the gas version, blades and no blades, there isn't much of a difference, right? So the conclusion there is that engine noise dominates everything. And that's really what we're finding. So interestingly, when you eliminate that engine noise, there's other noises that have always been there that begin to pop out. And that's become a bit of a problem for us too. We have to kind of chase down those, or at least make customers understand these new noises that they're hearing from their machines. So a bit of a double-edged sword, but also importantly, velocity. So we have users with hands on these machines, and they can be fatiguing. So we're also looking at the reductions that we see going to electric motors and reducing the vibration, and that impact on fatigue of our users. So that's a little bit of the why. This is just kind of an overview of at a very high level of how we're getting there. The top really kind of shows our current gas lineup. This isn't everything, but it kind of gives you an idea of the breadth of the types of equipment that we currently sell. We have about 90 active models, in our gas powered equipment, and that within that there's about 70 different engine part numbers, anywhere in the 5 to 25 horsepower range. So it's a bit of a mess, really, from a configuration management standpoint. Not a lot of commonality there. So when we look to electrify, we want to simplify as well. So our strategy would be to come up with hopefully 3 to 5 motor sizes, right, in the 1 to 5 kilowatt range, and 2 to 3 battery sizes in the half kilowatt hour to 3 kilowatt hour range, and try to create that commonality across the products. How we're moving forward with that is in 3 basic steps here at the bottom. Speed to market, which really is changing as little as possible, right? Get products to the market quickly, get feedback. So to do that, we're leveraging our existing gas designs, and we're leaning into the experience of the mean green mowers, their 10 years of experience to use as many existing pieces as possible and just put those together and get a product to market as quickly as possible. And we'll talk a little bit more about that in the coming slides about our field and brush mower that you can see here. Our next steps are really to go through system design definition. So trying to understand what the requirements really are for electrification. If we're going to optimize these designs, what are the power draw? What is the power draw for each of these machines under various conditions? And then beyond that, really looking at product design optimization. So taking all of that learning and trying to use more of a clean sheet of paper approach where we can really optimize the design of these machines for electrification. So in our speed to market, first approach is the basis of this is a large battery platform. So we're taking essentially some existing learning from Mean Green and applying it in a new way. So we've created an interchangeable battery pack that is really the first of its kind in large format outdoor power equipment. It's 2.5 kilowatt hour battery, up to 3 batteries in parallel. And that's really a departure from the commercial products that Mean Green had in the past. Had always used fixed in place batteries. So we've repackaged that, but we've really used a lot of the existing cell structure, the battery architecture, the battery management systems, all provided a basis so that we could get this product to market more quickly, focusing really just on the aspects of the removability of it. And then the anchor product for the platform is a zero-turn mower. This is a design that largely leans into existing commercial designs from Mean Green and really just scaling them down for the consumer market. And those they both launched this spring. So we really have that anchor of the platform in place. And really then we're working on filling out the platform further. So the first product that we really fully designed here in our Vermont facility is the field and brush mower. That did also launch this spring. And we were successful really in meeting that speed to market goal. We feel we reduced a typical 18 to 24 month timeline for development, compressed that down to 14 months, which we really were asked for 12. So we got pretty close. Thought we did a good job. And we had a goal of keeping 80 to 90% of the parts common. So really that's key in moving fast because that reduces our design and testing time. Sourcing strategies are largely in place, and our assembly line remains basically the same. So we were really ultimately successful, and I'll take you through the journey of how we got there in the next few slides. But a little bit of the key aspects of what we were trying to do with this project is we really were looking for run times on one battery. So we really want to be able to run this machine on one battery with 30 minutes in the toughest of conditions and 60 minutes in other conditions. And you'll see how that was one of our biggest challenges, along with some of the risks we identify down here in terms of retail price and motor and controller availability and other things that we struggled through. But as we started out, we came up with a design concept that ultimately allowed us to reach 85% commonality. So this slide just kind of represents what's new and what's existing. The new parts are in yellow. The basis of this really is the electric motor. We essentially removed all the gas components, but we left the belts in transmission in place. So we have a single motor here driving multiple points of power application. But that was the quickest, easiest thing to do. Essentially, we could drop, in this case, the InMotion RSM 170 motor pretty much directly in place of the same shaft location as the gas-powered engine. We had to add some components for the battery and the battery receiver to integrate those into the machine. We had some changes to the controls and the control panel at the top. We reused most of the mechanical controls, but did have to replace things like we had to add a display for battery runtime, and there were push button switches for the electrification that were required for minor controls. and then really kind of wrapped a bunch of sheet metal around it with a battery enclosure and hood to protect the electronics and to allow access to the battery. So again, quick and dirty, leveraged um, a lot of the existing design, and we met our goal of 85% commonality. Then we went to test it, um, and mixed performance, mixed results. Honestly, in the performance. So you can see that along the left here are the different types of conditions that we ran in. So this machine, has a lot of different uh, conditions that it runs in. So in saplings, kind of brushy areas, we did pretty well. 62 minutes of runtime. You can see that when you're looking at the chart, the RPM drops and recovers, but the torque and current remain pretty low. So our power use is good. When we get into medium density grass, we're kind of barely meeting that runtime. You can see that there are some dropouts in RPM. Torque and current are high, but they don't exceed the max threshold that you can see here in red. So we're okay. But when you get into heavy dense grass, it's a different story, right? We're getting consistent dropouts in RPM. The torque and current are above the limit, and our runtime's not meeting it. So we had to dig in there, and try to understand what was going on. So really, our conclusions from the testing were that some form of reduction in power draw was needed. We considered mechanical options, such as a side discharge on the deck, that would limit the mulching. So you're not cutting and recutting the material, which would reduce power consumption, but also isn't preferred because of the decrease that you'd see in cut quality. So really what we zeroed in on was some method of reducing motor speed, and that seemed to be the most promising approach. But it was unclear of how we would approach that, right? As we're climbing up this learning curve of electrification, well, what are the knobs that we can we turn here in the design? And did a lot of research, working with our partners in InMotion, collected a lot of additional data, and really looked at how we could thread that needle of RPM. And what we found was it is possible to increase the torque output and the battery runtime while reducing that motor RPM. And looking at the torque versus power curves of electric motors versus gas engines, we learned a lot. And this chart over at the right shows a difference also in the design of the motor, which can improve torque as well. So we went from an 8 turns per coil in the stator to 11 turns per coil. And also up the entire range of torque, and also looked at where we would stay in the efficient operating range of the motor. So through doing that, we developed a strategy to reduce the RPM. We did improve the runtime in dense grass, but we also really had to look at how that reduced RPM would reduce drive speed. So because we're only running one motor and it's running the blades and the drive system, we didn't have the ability to adjust those independently. So we had to make sure that we weren't dropping the RPMs so much that the speed became too low. And we also had to look at the impact of cut quality, because although torque's needed in many situations, just the sheer blade speed needs to be high enough to cut and recut that material, and get the cut quality that we needed. So there was a lot of testing and prototyping and tuning eventually of the algorithms that we developed within the motor controller. And we looked at whether or not we would want to do that in an automated fashion, or whether we would want the user to use some sort of turbo button or other other means of selecting that. But when we looked at it, the differences in performance were so low in a region where it didn't really seem like the operator would be impacted by it. So we decided that an automated approach was the best. That was the simplest to implement as well. So really, what we ended up doing was automatically reducing the motor RPM when high loads are detected, or only when the blades are turned on. So that was ultimately the solution. And in the end, validation of the final product showed that we met our goals. So overall, in the end, we met the expectations of performance versus the gas machine in all conditions. Our testing does show a minor performance degradation at reduced RPM, but again, not to the level that a customer is really going to find that as a degraded experience overall. And we did achieve our runtime goals. So we increased from the initial prototypes, we increased to 50 to 60% in all conditions over that initial prototype. And then we also found though that we really in managing runtime, we needed to manage temperature as well. And that was in thermal issues were concerns that came up later. As we got better at increasing runtime, we found that obviously the more you run the machine, the more heat you build up. So we attacked that mechanically with more venting of that enclosure around the motor and the battery. But we also developed algorithms to limit RPM when certain load conditions occur and when heat's rising in the motor. Because what we found is if you ran the machine hard, you would hit your thermal limits before you drained your battery, right? So obviously, in most cases it's better for the customer to continue to run the machine even if it's at a slightly degraded performance, and you can get the full runtime out of the battery. So again, without really making it obvious to the customer, there is management going on in the background to say, the number one thing here is to hit your runtime numbers. And if you have a 5 to 10% reduction in power at the end of that battery life, it didn't really seem to be, again, anything that would be noticeable to a customer. So ultimately, successful validation met our goals, and we're happy with that approach. But really moving on in the story, that turned out in a number of ways to be a very limited design, right? And really what we want to do is optimize for electrification. So really kind of have a bit of just a cartoon here that we use to just when we're talking about how we're moving into the next phase, defining the requirements for these machines, and we're really working around this triangle of motor selection, battery spec selection, runtime, but ultimately how that affects performance. And the top of the triangle really is that performance. And we're finding that they're not one-to-one trades, right? Every time you push on one side of this triangle, you affect the other. So that's really kind of this has kind of become our guiding beacon of working through these, trying to understand what the requirements are for each of these machines. So the approach that we took to that was to baseline a number of different of our products. So we took 8 different products over the course of last summer. We baselined them all using the same motor. This is again your RSM 170 motor from InMotion, our large battery pack that we developed. We've got a test rig here with the controller, some other ancillary electronics, and a backpack with a data collection laptop, or in some cases, some of that is off board. In our smaller machines, we had to bring the battery off board. But really using the same basic setup across the machines, so that we could gather data quickly and understand the power requirements under various conditions for these machines. None of this represents an optimal design for these machines in any way, shape, or form. It was a means to an end only. So this allowed us to collect data and compare machine versus machine, and in any given machine, its performance under different conditions. So now that we understood that we could collect data, we needed to understand what data we wanted to collect. So how do you really understand what this machine needs to do? So what we needed to do is define, limit and control the real world variables that our products see. So all of our machines see a tremendous amount of difference in what they're doing, depending on the user, the environment that they're in, the time of year. All sorts of things can affect that. But if we're going to base on the performance of the machine, we had to find a way to do that repeatedly. So really what we started out with was analogous materials, so that we could get controlled and repeatable test samples. So for instance, in a chipper shredder, cardboard strips equal leaves, right? Dowels equals twigs, and fence posts equals big branches. So we could define a specific size and repeat those testing. Um, and then through that, we could establish the power required for a variety of individual cases. So we would break down the machine, what the machine was doing into different types of operations. And we would gather short snippets of power data for that. And then that also verifies the bounds of machine performance. So what's the maximum torque required? What's the minimum required at idle? Those kind of bounds in the system as well. And we can take those chunks and we could build those up into real world scenarios. So estimating a typical job and what it would take to complete. So an example here would be if you drop a tree, and you're going to take care of that in your yard. What's the mix of work that you're doing? You're chipping and shredding small materials. You're chipping larger materials, and then you're shredding leafy branches and those kind of things. So going through and actually doing that job, breaking it down into what percentage of the mix we were doing that with, and then also adding in idle speed, because we realized, well, this is an indication of the work that you're doing. But if you're going to talk about time, and if our claims are going to be towards run time, there's some idle time in there, right? You're not constantly feeding this machine. You're reaching down. You're putting material in, and you're waiting for it to be processed, and you're reaching for the next piece. So there is idle time in there. So we had to take that into consideration as well. So one example, there of a chipper shredder. And then also, we had to take the qualitative assessment into mind. So we did do just straight up gas versus electric. So the lower right here is a video. I hope it works, but you can see we had a bunch of material lined up back here. You can kind of barely see. We had a bunch of users out there, ready to help us. And we had a gas powered machine here and its electric equivalent in place. And we really just ran a lot of users through it and got some qualitative assessment of what they felt, the gas versus electric performance was. So the basic conclusion, and you can kind of see that hopefully from the video, is that there really isn't much of a difference, right? The performance is generally the same. You can see that it processed the material relatively quickly in both cases. And in the look and feel of the machine for the user really wasn't any different. So that's kind of the idea for our test scenarios. Another example to go through in a little bit more in depth of the data that we collected was our walk behind mower application. This again was a setup with the RSM 170 motor. Allowed us to, that allows us to collect a lot of data through the motor controller. We went through a bunch of different tests under different conditions that you'd expect for a mower: side discharging, bagging, mulching, again, just transporting, right? Running at idle, moving from position to position throughout your yard, and going up and down slopes. And collected data in each of those cases to again understand what was going on in all of those various scenarios. This is an example of a poorly performing machine. You're seeing a lot of dropouts in RPM, struggling to meet the power requirements, and this was really telling us something about the design of the machine. The conclusions being in this case for the wide area mower, that it really struggled to match the performance of the gas version. And again, putting one motor in place and leaving the belt systems there proved to be too inefficient. And the recommendation is that you just can't do this with a single motor. The motor would be too large, it's inefficient. The motor itself is inefficient in most cases for what we're trying to do. And the inefficiencies of the belt system is just gonna be too much of a drag on the battery runtime. So really then going to the what if scenarios. Okay, so what would we do? And then going to two smaller deck motors, one driving each blade, and then a very small transmission, um, so individual motors in all cases, and then trying to build that back up to, okay, what would then we estimate the runtime to be, with that total amount of power required. And really, all this is doing is setting us up for future testing, right? The conclusion here really is just, hey, that's great, but now we've got to go test that and prove it out. But it did help us really understand where we might be in terms of motor size. So this is really just kind of a very high level chart. This is a distillation of many tests down into just, again, a very high level view, just showing how motors could be grouped. The choices for each application are really going to be driven by their individual performance. This really wasn't something that really, told us a lot about any individual design, but we did feel like it was important to gather all this data in one place and start to understand how these motors could be grouped. Again, if we're driving at commonality, we've got to keep our eye on commonality, and understand, hey, if we are making choices, if we do have a choice in motors, and we're on the fence of one way or another, if we drive towards a place where these motors are starting to group together, that makes sense, and that's going to help us in the long run. We also had to look at battery optimization, and we kind of started to look at this a couple of different ways. We initially thought that runtime was going to be everything, and it is for the user. But to get there, the machine has to be able to run on the battery that it's given, and so the discharge rate, or the continuous current that we're able to put out, really becomes the pinch point for a lot of these machines. And what we were trying to do was to make a single lower cost battery, but we also want to be able to run as many machines as possible on a single battery. So this chart was something we put together and worked through with our product development team to understand the trade-offs. So really just baselining cost in a relative manner against our existing large format battery, and looking at, as we reduce the size of the battery, right, the overall capacity, and therefore reduce the relative cost, we also have to keep in mind that the continuous current output of that battery is also going to be affected. And in this case, understanding the capacity of the cells and the architecture that we're using, at an assumed 1.6 C rate, is going to give us the continuous current draw that you see in this column. We looked at that against the average current draw that we estimated through the work that we had done on all of the various equipment, and then understood with different types of machines. So our wide area mower that you saw, a power wagon, a leaf vac, what would the number of batteries required be in all of these cases, as you begin to look at different sizes of the battery, and driving towards one, right? So we're green at a 1.2 kilowatt hour battery. We've got a number of different machines that can run on one. Where we're running on two, it may be acceptable. But if we drop down, in this case, we drop down to a 1 kilowatt hour battery, the lawn and leaf vac and the trimmer begin to look like they're going to need two batteries. But then when we dig in further, we start to look at, well, if they're drawing 35 amps and we're able to provide 33.3, is that a challenge that we can accept, in the long run? Can we get this machine more efficient? Can we push the battery a little harder potentially? So, ultimately, in the end, we did push towards a 1 kilowatt hour battery, and we are trying to solve this problem, at the machine level. We also began to look at batteries in terms of optimizing versus runtime. And again, this is kind of a very high level chart that again won't necessarily drive a decision on any individual machine, but does begin to show you the trade-offs. A little bit of a hard chart to understand, because it does jump around a little bit in terms of the number of batteries that you're dealing with. But each of these bands is the battery size that you saw on the previous page, and the kind of the dumbbells represent the runtime with a number of different batteries. And the trick here is that the number of batteries change a little bit as you go across the chart, because as you get into a larger battery, you're not going to need as many batteries to run the machine. So if you take, for example, the wide area mower, which is the blue, the first three entries are all between 2 and 3 batteries. So your runtime with 2 batteries versus your runtime with 3 batteries. Larger battery, still 2 to 3, right? Once you get up to a 1.4 kilowatt hour battery, it drops down. You can use 1 battery on that machine and still run it. So it drops down. So you sort of have to follow this chart, but it does give you an understanding, of where your trade-offs lie, and when you're making those choices in terms of, am I going to give a customer a smaller and therefore on an individual battery cost, cheaper version, but what is that going to do to my runtime, and ultimately how many batteries do you need to get there? We found this was a decent way of communicating with our product management team. So from there, we move into product optimization. So really going from um, you know these sort of quick and dirty, change as little as possible, use existing pieces, to let's start with a clean sheet of paper. Let's get some of the advantages of electrification, on the table, and really we're in this now, right? I can only report limited progress because this is where we are in the journey at the moment. But we have made some strides, and we are moving along. But the first step in all this was really just paper studies, right? We did these short design sprints, to really get a lot of conceptual designs on the table and evaluate them at a really high level, for how they trade off against one another in terms of electrification. So again, at a really high level, all of these design applications were looked at, and although all these products vary a little bit, in terms of their design, we could kind of look at them along the lines of these three basic strategies for, again, what we saw before, the direct replacement of a single gas engine with a single motor. Then we came up with a concept that potentially we could use a single motor that could be swapped from one machine to another, a potential cost reduction, or, again, with a platform concept of a battery and a motor being swapped from machine to machine. And then really ultimately the optimal design for electrification using multiple motors on any given machine, right? So the evaluation criteria were kept really high. Again, generalized, kind of you'll see in the trade-off study, kind of a high, medium, low approach. But that was in order to look at the similar criteria across the broad range of product applications. But generally, the bottom line here was what we were looking at was trading off and optimizing power generation, power transmission, and power application, right? And that's really the optimal, on any given machine, where are you using that power? And if you can actually eliminate power transmission, you're going to be the most efficient machine, and you're going to be the least complex machine. So single motors, where you need them, are really where you'd want to be, in terms of the technology. That may not always be, the best in terms of other factors, and that's kind of what we're seeing as we're going through it. But as an example, we kind of tee up, an existing machine. We look at what's gonna stay the same. So trying to keep the basic design of the machine the same in many cases, and changing the design where we need to eliminate those inefficiencies. So in this case, instead of a single engine here, some of the options that we proposed, and you'll see this on the next page, we started with these design options and these paper studies. We started with block diagrams to kind of break down where the interfaces are and where the trade-offs lie. And in this case, the strategies that were considered were a power head, again, a swappable engine that replaces the current gas engine and directly drives the existing impeller and mechanical transmission with all the belt systems in place. Then we looked at a complete electrical system, so no power head, individual motors. So you would have a separate motor directly on the impeller to drive that leaf vacuum system, and you'd have a separate electric transmission on the wheels, and then a kind of a hybrid approach where you'd use that power head to drive the impeller, but you'd have a separate electric transmission on the wheels. Again, trying to make use of this power head concept, but to see if there were interesting hybrid approaches to it. And we just represented those in block diagrams as a starting point to kind of, again, just kick off the trade studies. And where we ended up, skipping over a lot of detail, in terms of how we got there, we set up, again, very high level, simplified trade space. There's a lot of work that went on, in those 3-week sprints to fill this out. There's, tons of trade studies here that I'm not going to go into detail that happened in the background, but really just looking at the criteria along the left here in terms of, does it use the swappable power head? What's the runtime? What's the tool only cost? What's the total machine cost? So with battery or with power head, if that's the choice. What's our development time, right? How long is it going to take us? Because there's the things that need to be done to design and validate. And what's the complexity of this design, both in terms of, again, how long it's going to take us to get that design done, but also how's that impact reliability and other factors when it gets out into the user. So again, really bringing this up at a high level and just looking really kind of at a high, medium, low approach. This again isn't driving a final decision. What this is really doing is setting us up to say down select and look at these further in terms of actually developing prototypes and going back and exploring some of these assumptions and understanding more about the machine. And that's really where we're at today. We've gone through 7 or 8 of these paper studies, and we've got a shop full of breadboard prototypes at this point, which are in various states of testing, and we are collecting data to ultimately inform the projects that we're kicking off to fill our product pipeline with optimized electrical designs. So that's where we are today. So conclusions, really that is our next steps, right? We're continuing to build prototypes and down select those options from the design sprints. Some of the other things that we're looking at is motor RPM. We really got to get out of this paradigm of 3,600 RPMs. That's where gas engines typically run. That's what a lot of our machines are designed around, but that's probably not the optimal speed in many cases. So we are branching out, looking at different motor speeds. We're also looking at voltage. We kind of fell into the 48 volt range based on Mean Green's experience, and largely theirs was driven by market availability. But we're finding, as we saw heat rise be an issue in our first project with the field and brush mower, our current draw, itself and the heat that it creates, that might need a rethink, in terms of what's the best voltage. It's difficult when you start to choose a battery and choose a voltage. You want to reuse that battery. That's a tough one. And we've got to manage that carefully. And also looking at the electrical system optimization. So finding cost-effective solutions for electrical components other than the motor and controller, fuses, contactors, all of these things add up in terms of cost, and on our lower price point machines, they begin to be a bit of a driver. So we're looking at ways to create custom controllers where we can begin to integrate some of those discrete components into an overall custom board, which also allows us a lot of flexibility in terms of our controls and displays and other things. So we can get some common I/O going across from one machine to the next, and look at the logic functions that we need to do some of the power management, and again reuse those from machine to machine would ultimately be the goal. And in terms of lessons learned, really, again, we're still in the middle of this. So we're continuing to learn every day. But what we're finding so far is that electrification unlocks a far better user experience than we thought it might. And really, in the long run, we hope that's gonna change the market, right? the features that we can provide, easy speed adjust, independent drive and tool speed, reversible. You can reverse an electric motor a lot easier than you can a gas engine. All of these things build up a better user experience, and overall the machine's just more pleasant to operate. So what we're finding though ultimately is that batteries are going to dominate our cost structure again, especially on our lower price point machines. It's a problem, and cost and performance need to improve on those batteries, or a lot of these products right now just really aren't viable in the marketplace. And really another step in making them viable in the marketplace is educating our customer base, right? Making them understand what's the value proposition. When we survey customers, they'll tell us, well, I really don't like having a lot of batteries. I wouldn't want to have 4 small batteries. I want one big battery because it's easier to manage. But are you willing to pay 4 times as much for one battery? Or is it more attractive for you to be able to buy 4 batteries over time? So these are things where customers don't always know what they want, or they don't know what it means. And we, I think, as an industry, are starting to confuse them with marketing claims that don't really mean much, right? When we start to say, we have a 96 volt system. Well, is a 96 volt system twice as good as a 48 volt system? No. But does a customer understand that? Well, no, not in most cases they don't, right? So they don't understand what the numbers mean. So that's not helping us. That's not helping us, really across the industry. So I think we need to get real, about what we're saying, and try to educate our customers, because that's going to help everybody in the long run. So that's where I end the slides. So I'll throw it back to Zach, and I want to thank everybody for attending today, and thank you for your time.
Thank you very much, Mark. It's been a pleasure hearing about your journey through this. We do have a few questions. I'll try and keep the answers brief given
Sure.
the timing here. So the first one is asking about the batteries, and this may get into some IP issues. I'll let you decide that. But
Okay.
are you using 21700 size cells or something else? And which manufacturer provides your cells?
I'll answer some of that. We are using cylindrical cells. They are 21700s.
The next one is talking about the dealer and retailer response to these new products. Do you have any feedback from the dealers or retailers on the new electrified products?
Yeah, I mean, we're really just getting them into the hands of the dealers. Some of the mean green dealers are used to dealing with electrified products. Our existing dealer base isn't so much. So we're really, it's very early days, right? We really just launched these products in February. So we are just beginning to gather feedback from the dealers at this point.
Okay. And then one more came in. Speaking about voltages, do you foresee this segment moving to higher voltages like 400 plus to reduce thermal heat dissipation, lower current, and reduce the cost of cabling and connectors?
Yeah, all good trade-offs, right? And we are seeing that. I don't know about 400 volts. I think that may be high. Certainly there's sort of a limitation now at 60 volts. That puts you in a realm of having to do more testing to prove safety. So jumping over that 60 volt hurdle is likely to happen. And I think in some cases, we will see the need for that, because it does reduce costs in other areas, as the questionnaire indicated. I don't know that 400 volts necessarily makes sense for small power equipment. Perhaps on some of the larger ride-on equipment that may get there, but I would say I wouldn't think that'd be a choice that we necessarily make for handheld or walk-behind equipment.
Yep. And then one last one here. What are the challenges related to charging in the outdoor power equipment space, particularly when the battery capacities are large?
Yeah. I mean, the biggest challenge with charging is cost. I mean, typically what we've found is you can kind of charge a battery as fast as you want, within reason, right? As long as you're willing to pay for it. So that's really, again, where we're really relying on initial customer feedback to help understand, how long are they using these batteries, and then how long is their overall job period. So is it important for them to quickly recharge, and are they getting back out into the workspace, or are they using this battery and it lasts them the period of work that they need. Let's say they're doing a cleanup job, and it's taking them an hour, and they're basically, if they had to recharge their battery overnight, it doesn't really matter, right? So at some point, if it's 1 hour or 4 hours, or once you get to 6 hours, 8 hours or 12 hours isn't really that much of a difference, right? So we're really trying to understand this sort of like quick turn back into the field need versus, okay, if we're really talking overnight, then anywhere between 6 and 12 hours is probably okay. So the jury's still out. But it is definitely, it definitely goes through cost, as I'm sure anybody who's looked at chargers would understand. And that's really where we, again, need to understand customer acceptance of that.
All right. Very good. Mark, thank you very much for your time here today. We appreciate the topic and the in-depth presentation here. And thank you all for attending. Please join your next session through the lobby.
Great. Thanks, everyone.